Okay, let's go. Today I'm going to go through 5.3 and with much confidence that you can do any questions related to Kirchhoff's law. Yeah. Correct or not? Yanin? Yeah, they're very confident now. That's good. So what we're going to do today is 5.3, and 5.3 only focuses on the main chunk is basically the batteries, the performance of batteries. Now most of the time when you do it in secondary school, we draw it this way, like battery connected to a resistor, it looks like this. EMF E, resistor R, current will be equals to E upon R. Correct? Nice. It is. So we always assume that batteries are ideal and they don't have this thing called resistance, which is impossible. Now in order for something to not have resistance, there are only two ways. Either it's a superconductor or there's nothing at all. Then there's nothing, so there's no resistance. So it is impossible because this is definitely not a superconductor, neither is it nothing. So in fact, if you break down a battery, I don't know whether you have played with this before, do it safely if you want to do it. If you open up a battery, you see that actually there are some chemicals inside. Yeah, so electricity flows through the chemicals, there will be resistance. And how do we represent the resistance of a battery? We do it this way. And we box it up to tell you that this is a battery. And it is connected in series to the battery. So that's how we represent it. Now you don't see a battery, a 1.5 volt battery having something connecting out. So this is just a model. This R over here is actually inbuilt into the battery. So how does it affect the performance of the battery? And I'm going to stretch you a little bit to go to the ASP part of things. Not necessarily in IB, but I thought it's always good for you to know. So let's start out with the very simple stuff. Okay? Now, if this is 0 volts, I'm going to show you later that it doesn't matter what volts this is. Now let's start out with 0 volts first. Now do you agree that this part is E volts? Because the battery is E, right? So 0 to E. Now, the current in the circuit will be equals to, say, if the current in the circuit is I, do you agree that this PD over here will be IR? Now which point has higher potential, this point or 0 volts? Current always flow from higher to lower or lower to higher in a resistor. Higher to lower, yeah, correct. So this, if this is 0 volts, since the potential difference is IR, this will be IR volts. Agreed? Now if I were to put a voltmeter across, what will the voltmeter register? E, higher than E, or lesser than E? Lesser, yes, right. In fact, if you take a careful look, potential difference, the V terminal of the battery is actually E minus IR. This is what the battery will give to whatever you connect it to. This is what the load, we call it the load, will receive, which is obviously lesser than E. So it is bad. No choice. You can't run away from it. The 1.5 volt battery that you have, it's about 1 ohm resistance. So that's the reason why when you connect wires to the end, to the two ends of the battery, it doesn't explode. But you try that on the accumulators, your daddy's car. Don't try it. Because if you try it, the accumulator's resistance is about only 0.1 amp. Yeah? 0.1 amp, 12 volts, how many current? How much current?
Oh wow.
120 amp. And what's the power? Power is equal to I squared R. Right? 120 squared times 0.1. Kababooms. Yeah. And your daddy's car, your daddy won't be able to drive. Oh, sorry, I'm being sexist over here. Your daddy or mommy is not going to be able to drive you to school. Yeah. Okay. So it's internal resistance is bad, but sometimes it protects us. Okay. It is intentionally designed with certain internal resistance so that you don't die if you short circuit the battery. Now, if I were to convert this to a rheostat, a variable resistor, do you agree that by changing the value over here, I'm going to get different value of I and V? Make sense? Now, this is what I want you to think about. If I were to plot Vt against R, how would the graph look like? It's a curve, okay? Anyone? Okay. Anyone else? How would the graph look like? Think in your mind. Y equals to mx plus c. Does it go this way or does it go this way? How?
So this small R.
Sorry?
Oh yeah, that's
This is small r. This is small r.
So yeah, are you changing the small R?
Oh, okay, sorry. This is not I. How am I doing? I. So how will you look like? First of all, straight line or curve? Straight line. Negative gradient or positive gradient? Negative gradient. So how do you know that? Yeah. Some of you are very hesitant, but you actually get the right answer already. So what's the value over here?
Equals to small r.
This one?
Right, like
E, yes, correct.
Oh.
This is your EMF of the battery. And this one, the gradient will be equals to? Excellent. So this is how we find the internal resistance of the battery, and this is how we find the EMF of the battery. Okay? This is the experimental method you use to find the EMF and the internal resistance. Okay? Oh, come on, no, yeah. Please, this is a little bit simple. Why? Okay? But something interesting, I don't know whether you find it interesting. For me, I think it's really interesting that at this current, where the current is equals to E upon R, you actually have no EMF. You actually have no effective PD. I don't know whether you find it interesting. That means the battery is actually using energy, and all the energy that the battery is giving is being dissipated in the internal resistance. No energy is given out to the external resistor, which is actually quite interesting if you think about it. Yeah. And the only way that you can actually have, the only way that you can have EMF operating at its E is where there is no current. So you never have this.
So is that negative?
Negative R. That's right. This one.
Like when you go down,
This one.
does the graph extend to the negative region?
No. If it extends to a negative region, it means that it actually is a reverse.
Reverse.
It doesn't. It doesn't. Yeah. So there's mathematical outcome, but there's no physical debug. Okay. It's like when you solve for equation, the k goes to negative kind. Cool. So let's extend this a little bit more. This is one equation that you need to know. The other form of the equation comes from this actually as well. So Vt is equals to E minus IR. Can you see that I is equals to E upon R plus R times R? Yeah. And therefore, if you common denominator it, it will become like this, and it will be familiar? Potential divider formula. Can you see that this E is actually divided between this and this, so that's why it's divided. Potential divider formula. The E is split between the big R and the small r. Which makes sense as well. So the only way for Vt to be equals to E is where the big R is very big compared to the small r. Now when the big R is very big compared to the small r, what is the current?
Zero.
Almost zero. So it tallies with what we talked about. Now we need to solve question. Okay, knowing equations is not good enough, you need to apply. So let's take a look. Given these two sets of data, find the value of the EMF of the battery and the small r.
So the big R, the big R refers to that single component.
Big R is this one. Small r is the one that. you get E to be 20 volts, and then small r to be 10 volts. It's mathematics already. So if you substitute these values in, it will be 16 equals to E times big R divided by big R plus small r. 10 equals to big E, 10 over 10 plus R. You take equation 1 divided by equation 2, you're going to get 8.5. E cancels out. This will be 40 divided by R plus 40. Equals 10 plus R divided by 10. 4.2. 2.5 equals to R. Cross multiply, you get the answer. Now I'm going to go to something more difficult. This is ASP part because it's going to require differentiation. Okay? But before I go on to that, two of you okay? Facing some resistance? Internal resistance? Guys, okay? Okay? Okay, good. Questions? Okay. Cool. Alright, so let's take a look. You have a big R over here and E over here. Can you derive an expression for the power of the big R in terms of E, small r, and big R? Then what you do is, I want you to differentiate this expression with respect to big R. And then guess what you're going to do with the expression? Sorry? In any graphs, obviously this is going to be a curve. So in any curves, what is of interest? No, you need to differentiate. Any curve. Tell me, what are the points of interest?
Highest, lowest, minus.
Exactly, turning points, right? So,
Oh.
then you find a relationship between R and R. Okay? Give me a try. You find something. Allergy is what now? It's going to be back next week or what? It's attending to some family events. Yeah.
Is he going back or what?
I guess so. Fortunately, we videoed the lessons. So is there a day that we're going to all face the back? Actually, I can write on the back as well, right?
Oh, that's true. Like if
So you can. It's possible, right? It's going to be
April Fool's already.
Oh man, oh dear. You didn't see this, oh dear.
They just use like a white towel.
We always got the all-powerful toilet paper. They can wipe away all kinds of shit.
Actually, it's not bad for writing, right?
Okay, it is okay. It's just that you have to. Oh man.
So water will help. Glass will be good. Hey. Okay. What the heck? You can't see R.
Okay, in case you don't know what's happening over here. Oh, what is the big bomb here? What's happening here? What on earth? I'm going to DD1. Okay, basically I asked the class to come up with an expression for power as a function of big R, small r, and E. And then I asked them to differentiate the expression and set it to be 0. So you're going to find an expression for R and R relating the two of them where there is a turning point. Because in any curves, the place of interest is in the turning point. Yeah. So go ahead, enjoy your quotient rule. Still remember your quotient rule? Yeah. Quotient rule. You know that? Differentiate the top times the bottom minus differentiate the bottom times the top divided by bottom square. Bing bong biang. You're going to find that expression is really beautiful, really, really neat.
Something from it's wrong, obviously wrong. Never mind.
ER, okay. It's actually, remember we got an expression for the V across R to be equals to, it's actually this. Then this V squared, that's why it's V squared divided by R, power. Power is V squared 1.
Oh, you don't take
E, as in?
oh.
Oh no, you don't take E because the E is split between this and this, so you want to find the power for this. So you take the PD across here, yeah, not the whole circuit. Yeah, not the whole circuit. So let's see how you differentiate now. So you get PR is equals to E squared R divided by R plus R squared. So you differentiate the top. It's E squared R plus R squared minus 2R plus R E squared R divided by R plus R4. So if this is equals to 0, E squared R plus R squared equals to 2R plus R E squared R. Maximum power. If you learn electronics in the future, you'll find this very interesting phenomena where the resistance of your load, if it is equals to the resistance of the source, it will transfer maximum power. So actually it is good for your source to have a little internal resistance, because if your source has very low resistance, that means that the load in order to receive maximum power needs to be designed with very low resistance, which is very difficult. So it is actually good to have a little bit of resistance, so that it's easier for people to match your source. Yeah, it's called impedance matching. In loudspeaker, in any electrical system, this is a very important thing. Otherwise you may end up with a very powerful amplifier but just cannot transfer power. But there is a dilemma. The dilemma is this. Let's take a look at the efficiency of this system. If you have this R, big R over here, and you have the E, can you see that the power total is equals to I squared big R plus small r? I squared times total. The power of your load is equals to I squared big R. So the efficiency of the system is equals to I squared big R over I squared big R plus small r. We strike this off. So even though you have maximum power transfer when R is equals to R, you only have 50% efficiency. How do you have 100% efficiency? You make R really, really big, and you make R really, really small, then you have maximum efficiency. But the problem is, if you make R really, really big, it means that the current is going to be really, really small. It means that your power will be very, very low. So the only way for you to have maximum efficiency is to have zero power. So the most efficient way of doing work is to do no work. Oh, yeah! So whenever you're sleeping and resting, if your teacher say, why are you not doing work? Actually, I'm working very efficiently. Try that and see what happens. Technically not wrong, but you will be in the wrong. Yeah. Yes. Yes. Go ahead. I love dumb questions. Excellent question. No one asked, but you asked. Actually, you just need to differentiate it another time. Second differential. Then you find that it's a negative value. The d2p, d2p, dr squared.
Is it always?
It will be maximum. If you plot the graph using a GC, you'll find that it's a.
So another term.
Yes, go
How
ahead.
did you differentiate them?
How do you differentiate a rule? Remember quotient rule? If we got this divided by this, we differentiate this times this one, which is this. Then minus differentiate this times this. Then divided by the bottom square.
Think
You know
it's
what?
Sorry, sir. Dumb question, but like, I'm gonna use this anytime. Like, will you use this?
In IB, no. No worries.
Sir, dumb question.
Yes, yes.
If power
Suddenly every question a bit
if
dumb,
the
yeah.
power across the resistor is I squared times R, but the result we derive from this differentiation is when big R equals to small r.
So you're getting
But
a call.
when small r
You're getting
is
what?
A call from 911-63766.
Oh dear, I think it's I think I know. I'll pick it up in the really.
r negative.
Yeah.
But when small r is 0, then I squared is maximized. So P r directly maximized.
Hang on, I didn't follow your I didn't follow your train of thought. So you're saying that when power is equal to I squared R.
Small r is
Yes. But okay, the thing is that when big R becomes big, okay, I mentioned that when in order for efficiency to be maximum, big R has to be really, really, really big, right? But the problem is that when you have a big R over here, then you're saying that this will be very, very big. But actually no. When you have this being very big, this becomes really small. And because this is a square, this is a non-square, the effect is that this is bigger than this.
So what if I have small r equal to 0?
Small
I mean,
R
small
equals
r
to zero.
small. I mean small. But from the result, by right it should be equal. But what if I have a really really small r?
So you're saying that what if you have a small R, then in order, then depends on what you're emphasizing. If you want to have maximum power transfer, then your big R needs to be equally small. Which is what I was saying just now. If you have a source that has very small input impedance,
Yeah,
then
it's
you will have an issue.
mathematically proven. But for the from the equation where we start, big R equals to I squared times big R. If the small r is very small and big R isn't small, then I squared is maximized.
I don't get your point.
If big R is a
Are you trying
constant,
to optimize power or are you trying to optimize current?
I want to maximize power.
If you want to optimize power, then we got the expression for the power already, right? Which is this one. The power of the load, not the power of the internal resistance. The power of the load.
Yeah,
Yeah.
power
So
should be equal to small r if big R is equal to small r.
so what's the point? I'm still not getting the point. So you're trying to say
If I only look at r, p equals to I square r, it doesn't look like r when big R equal to small r is maximum.
You can't,
That's
because
it.
from this you cannot conclude that it's a maximum. The only way they can conclude that it's a maximum is when you have to
Yeah.
substitute values that is not. The manual way is to substitute values where big R is not equal to small r and then compare the power. Or more rigorously, you have to plot out the expression. You're going to see that it maximizes when R equals to R. You give some values. Say for example, you put small r as 2 ohms. 2 ohms over here. Then you plot this equation as a function of R. Then you see the whole graph will peak at 2 ohms. That's a more rigorous way of testing it. You can't see from this equation that you will peak at this. Yeah. There's a reason why we need to differentiate to find rigorously where is that point. Because you can't see it or reason it out kind. Yeah.
What's like the smallest value you can give a resistor?
The smallest value.
So a resistor.
I don't think there's a bottom limit.
So you can
Is
just
there
make
a
it
bottom limit?
small.
It's zero lor.
You can make it
Superconductor zero.
Can you make it 0.0001 that kind of thing?
Of course you can. Depending on how long your conductor is, depending on how thick your conductor is. Right? Of course you can.
Then wouldn't the efficiency be quite high for that?
Again, which one?
For like if your small r is like superconductor.
Superconductor, yeah.
So it will be very high, right? The efficiency.
Of course. Makes sense, right? If your this is zero, then your efficiency will be really high, regardless of your R. Yeah, we're talking about real world case where R small r is not zero. But if small r is zero, then it will be 100% efficient. But we're not talking about wires, we're talking about source. Yeah, it's not possible. I don't think we have a super source yet. We only have a superconductor. We haven't gotten a source with no internal resistance. How do you have a source with no internal resistance? There will be wires, right?
Is it not
There
low,
will
but
be
like very small?
Yeah.
But like a very small value, not zero.
Small is possible, but zero for sources, I haven't heard of it before. Yeah, I haven't heard of it. It's always very small.
Well, actually, I think
Any many questions?
Superconductors, did they actually say resistance equals to 0?
Resistance what?
Equals to 0 for superconductors.
Yeah, it is equal to zero.
It is.
So if you go to CERN, If you go to CERN, there's another way I'll share with you. There's another way you go to CERN. So if you go to CERN, that's the place. The reason why I quote that place is because that's the place where it's the place where superconductor is present in the largest scale. It's a 27 kilometers circumference length of superconductors. And why do they need superconductors? Because they pass 13,000 amps. And why do they need 13,000 amps? Because current produces magnetic field. And magnetic field bends the particles to go around. Yeah? So they need huge magnetic field, so they need huge current. Now, 13,000 amps. If you have 1 ohm resistance for the whole 27 kilometer, imagine a 27 kilometer of conductor, you only have 1 ohm. It's a very almost impossible way to achieve with normal material. 13,000 squared times 1. 169 megawatts. And that's just for 1 ohm. If you have a 10 ohm, it's 1 gigawatts of heat.
Wouldn't that like melt the
Kabooms! Explode! Not melt, explode! That doesn't melt, that explodes. So you need superconductor. Yeah. In fact, one tube, you see, one tube from here, there to there, one tube costs 4 million euros. And predominantly, it's in running the superconductor, in running the CERN, most of the cost goes in cooling.
Oh, yeah.
Most of the cost goes in cooling.
so the cooling system never fails.
That whole thing won't work already. It will explode. I mean, because you're passing 13,000 amps, and if it suddenly switches into a non-conducting state, right? Oh, that's it. Explosion. It's explosion. Not melting. It's
More
explosion.
than explosion.
Kabooms.
So like worse than the nuclear reactor.
No, not that bad.
No,
Nuclear reactor is much more.
but this is nuclear reactor.
It's enough to cause disruption for a few months there. That was what happens when CERN was turned on for the first time. There was a mini explosion because of this issue. Yeah, and the whole thing had to be replaced, and yeah, it stopped for a few months because of that. Yes, to me, CERN is really amazing, not because of particle physics, not because of, it's partly because of the physics, but also to me, I think it's always is the engineering behind. It's just amazing. You can manage 27 kilometers of superconductors and all the engineering things that goes inside. It's just amazing. What human beings are able to. Sorry?
It has to be, right?
Yeah, in fact, they're building a super large hadron collider, 100 kilometers in circumference. They're thinking of, but of course, it's this.
It's under the city.
It's under the ground. That's correct.
So when you visit, you go underneath.
So wait,
Because above ground is too expensive.
So do you visit the thing under the?
Yes, this year we're very lucky. We actually went into the cavern where they have the detector. Because the beam wasn't running, there wasn't any X-ray. So we can actually go into the cavern where we saw the detector.
Oh yeah, yeah.
Yeah, I posted the picture here. Like, it's amazing. First time in 6 years. So this group is really lucky.
So
Really,
also
really
very
lucky.
We're not even going.
Uh, then first time in 7 years, yeah. Yeah. Okay, so I think we're done, and I don't know why I'm recording this, but okay.